Right, so we're doing now section 1.5 of the textbook, which is the lesson on continuity. Today we want to look at this idea of a continuous function. It's very important for functions that we study to have this property. Otherwise, there's not much that we can really say about them. So we want to understand what it means for a function to be continuous. We want to be able to demonstrate that certain functions are continuous. And we want to discuss and use an important theorem called the intermediate value theorem. That theorem can be used to show things like a function must take a certain value or equations must have a solution. So let's remember the definition of limit because it's wrapped into the definition of continuity. We say that the limit of f of x as x approaches a equals L if we can make the values of f of x arbitrarily close to L. That means as close to L as we like by taking x sufficiently close to a. So how close does f of x need to be to L for you to be satisfied that it's L? I can get it that close by taking x sufficiently close to a. And last time we looked at some very basic limits, such as the limit as x goes to a of the identity function x. We learned that as x goes to a, x goes to a. And we learned that if you take a constant function, f of x equals c, as x goes to a, the constant function c goes to c. It doesn't care what x is, it's a constant function. And then we looked at ways that limits can be combined with the rules of arithmetic. The first of these rules is that the limit of a sum of two functions is the sum of the limit of those two functions. The limit of a difference of two functions is the difference of the limits of those two functions. The limit of a product is the product of the limits. And the limit of a quotient is the quotient of the limits, provided, of course, we don't try to tell a lie and divide a function's limit by 0. So as long as that denominator function doesn't have a limit of 0, it's all right for us to divide the two limits. All right, so that's what we did last time. Now I want to launch into today's discussion with a few questions for you to ponder. Here's a question. At some point in your life, you were exactly 3 feet tall. That's a true or false question for you to ponder for a bit. And let's think about reasons we might decide that that question was true or false. How could it be false? Well, we didn't measure ourselves every day, and we may not have had a day in which we measured ourselves and discovered that we were exactly 3 feet tall. On the other hand, I know that I'm taller than 3 feet now, and I don't remember growing, an inch at a time, so at least there must have been some point when I was exactly 3 feet tall, even though I don't know when that actually was. All right, there's arguments on both sides of that question. Next question. At some point in your life, your height in inches was equal to your weight in pounds. Now, you probably know your height in terms of feet and inches, and so you have to convert that to inches, and that gets you a number. I'm 5'10", so that number would be 70 inches tall. And I'm a little bit heavier than 70 pounds. And you're probably around the same. So obviously now my height is not equal to my weight. But was it possibly true that at some point my height or your height was equal to my weight or your weight? Okay, ponder that for a little bit. That one seems kind of reasonable too, although it's worth considering. Next question. Right now, there are a pair of points on opposite sides of the world measuring the exact same temperature. The exact same time, 2 points on the opposite sides of the world having the same temperature. So if you drilled a hole from here all the way through the center of the Earth, coming out on the other side, measured the temperature on both places where that line comes out, you would discover the exact same temperature. Is that possible? Now that problem seems so complicated as to be impossible. How could we ever know that? How could we check that? How could we have 2 points on opposite sides of the globe with the exact same temperature? Well, all of these questions are applications of an important theorem that we'll talk about today. So the big concept of today is the idea of continuity, or for a function to be continuous. Last time when we looked at the limit laws, we learned this property, and we called it at the time the direct substitution property. If f is a polynomial function or a rational function, and a is a point in the domain of that function, then the limit as x goes to a of f of x equals f of a. In other words, the limit of the function at a point is equal to the value of the function at the point. That makes calculating the limit incredibly easy because all you have to do is directly substitute x for a. All right, and that property was enjoyed by polynomial functions and rational functions, and also some of the other functions we know, such as trigonometric functions, logarithmic functions, exponential functions, and many algebraic functions. So that property is so useful, it's worth giving its own name. Any function which satisfies the direct substitution property at a point is called continuous at that point. So here's the definition of continuous. Let f be a function defined near a point a. And we say that the function is continuous at a if the limit of the function at the point equals the value of the function at that point. And we say that the function is continuous, period, if it's continuous at every point in its domain. So continuous at a point means that the limit of the function at a point equals the value of the function at the point. And continuous without any modification means that it's continuous at every point a in its domain. Now on the right here we have a picture using the error and tolerance game, what it means for a function to be continuous at a point. The limit of the function equals the value. So no matter what horizontal band is drawn around the value f of a, I can draw a vertical blue band around x equals a, which will squeeze the graph inside that horizontal band. Okay, as we look again at the equation which is in the definition of continuity, we see that it has some important constituents to it. First of all, to be able to say that the limit of the function equals the value of the function at a point a, well, we have to have a limit at the point a. Without a limit, we cannot decide whether the function is continuous. By the same token, without a value to the function, we cannot say if it's equal to the limit of the function. And so that means a needs to be in the domain of the function in order to determine if the function is continuous at that point. So there has to be a limit to the function at the point. There has to be a value to the function at the point. And these two values have to agree. They have to be the same for the function to be continuous. Now, if we look at some of the things that we proved in the last class, things about limits of functions at a point, we can rephrase them now in terms of continuity. We know that a polynomial function has the direct substitution property at every real number, so now we can say that a polynomial function is a continuous function. No matter what polynomial we have, we know it's going to be continuous at every point. And the same is true for rational functions, except for the fact that rational functions don't automatically have their domain all real numbers. There are points which can be excluded from the domain of a rational function if you have a possibility of dividing by 0. So a rational function is continuous on its domain, which may not necessarily be all real numbers, but is probably real numbers minus a few points. Okay, how can we show that a function is continuous? Let's look at an example of doing that. We'll take the function f of x equals the square root of 4x plus 1, and the goal is to show that f is continuous at the point 2. Now how do we do that? To show that the function is continuous at 2, we must show that the limit of the function as x approaches 2 is equal to the value of the function at 2, that is f of 2. So what is the limit as x goes to 2 of f of x? It's the limit as x goes to 2 of 4x plus 1. This is a limit of a square root, and we have a limit law for limits of square roots. We can say that the limit of the square root of something is equal to the square root of the limit of that thing. So we have the square root of the limit as x goes to 2 of 4x plus 1, and 4x plus 1 is just a nice linear polynomial function, so the limit of that is equal to the value of 4x plus 1 when x is equal to 2. 4 times 2 plus 1 is 9, so I'm trying to find the square root of 9, which happens to be 3. And as I go back to the function, if I plug in x equals 3, what I get, x equals 2, what I get is 4 times 2 plus 1, 9, square rooted, which is 3. And so what we've demonstrated is that the limit of the function at the point 2 is equal to the value of the function at the point 2. Therefore, this function is continuous at 2. And each step in our equation here comes from a particular limit law. Okay, building from that last example, f of x is still the square root of 4x plus 1, at which points is the function continuous? At which points a can we say that the limit of the function at a is equal to the value of the function at a? Well, there wasn't anything particularly special about the point 2. If we had tried the previous example with the point a equals 3, we would still get that the limit of the function at 3 equals the value of the function at 3. So let's show how that would work. Let a be any number which makes this thing inside the square root positive. So as long as a is greater than negative 1/4, then the limit as x goes to a of 4x plus 1 is equal to 4 times a plus 1. If a is greater than negative 1/4, then 4a plus 1 is greater than 0, which means it's OK to take its square root. We can always take the square root of a positive number. The limit as x goes to a of f of x will be the limit as x goes to a of 4x plus 1. The limit of a square root of something is the square root of the limit of that thing, provided this limit exists. And it does because this is a polynomial, and we've computed its limit up here. So the limit as x goes to a of 4x plus 1 is 4a plus 1. We want the square root of that, and that is identically equal to f of a. So what we've shown is that if a is any positive number, or any negative number as long as it's greater than negative 1/4, then the function is continuous at a. Now what other points should we consider? If a is less than negative 1/4, then 4a plus 1 will be less than 0 instead of greater than 0. And of course we can't take the square root of a negative number. That's not a real number. So we can't say that the function is continuous at a number like negative 1, because negative 1 is not in the domain of the function. So anything greater than negative 1/4, the function is continuous there. Anything less than negative 1/4, the function is not continuous there because it's not defined. The only other point to consider is the point a equals negative 1/4 by itself. Now, if a equals negative 1/4, then 4a plus 1 is equal to 0. And we can take the square root of 0, that's 0. But what we can't do is take the limit as x goes to a of the square root of 4x plus 1. And that's because if we're taking the limit as x goes to negative 1/4, we have to consider points to the right of negative 1/4 and points to the left of negative 1/4. Now to the right, it's fine because 4a plus 1 will be positive. We can take its square root. But as we just discussed, if x is less than negative 1/4, square root of 4x plus 1 is not a real number, so we can't take the limit from the left. So we can't say that the function is continuous at negative 1/4 because we cannot take the limit as x goes to negative 1/4 of f of x. That's not quite the end of the story, though, because we can take the limit from the right. From the right, 4x plus 1 is positive, the square root exists, and because of all of our limit laws, the limit from the right as x goes to negative 1/4 is equal to the value at negative 1/4. So we can't say that the function is continuous at negative 1/4, but we can at least say that it's continuous on the right. And we're sort of making this up on the fly, but what this means is that the limit of the function from the right is equal to the value of the function. Okay, so it's not continuous at negative 1/4, but it is, almost continuous as it possibly could be. Okay. So all of the laws that we had for justifying limits, limits of sums, limits of differences, limits of multiples, limits of products, limits of quotients, carry over to limits about continuity. After all, the statement that a function is continuous at a point is really just a statement about the limit of the function at that point. So all of those limit laws give us laws of continuity. The limit of a function, limit of a sum of two functions is the sum of the limits of those two functions. Therefore, if two functions are continuous at a point, then the sums of those two functions will be continuous at that same point. Same thing for differences, f minus g, multiples, constant times a function, product of two continuous functions will be continuous, and a quotient of two continuous functions will be continuous, again, as long as we don't try to divide by 0. Okay, let's look at how you might prove that first rule, that the sum of two continuous functions is continuous. So let's assume that f and g are functions which are continuous at the point a, and what we want to show is that the sum of those two functions as a function is continuous at the point a. That is, we want to show that the limit as x goes to a of the function f plus g is equal to the value at x equals a of the function f plus g. Well, let's take a look at this left-hand side. It's the limit of a sum. We want to find the limit of the sum of f plus g of x. Because we have limit laws for addition, we can write that in terms of the limit of f of x as x goes to a plus the limit of g of x as x goes to a. This is provided that these limits do actually exist. But we actually do know that they exist because we have assumed that the functions are continuous at this point. So we know that the limit as x goes to a of f of x is f of a, and we know that the limit as x goes to a of g of x is g of a. Since the limit of these sums of these two functions is the sum of the limits of these two functions, we have that the limit is f of a plus g of a, which is exactly what we would want it to be, because that's f plus g at a. So in summary, we've shown that the limit as x goes to a of f plus g of x is equal to f plus g at a, and that this sum of these two functions is in fact continuous. And for all the other situations, the proofs are pretty much identical. If you want to change this plus to a minus, you'll have shown that the difference of continuous functions is continuous. Change this to a multiplication sign. That shows that the product of continuous functions is continuous. Change it to a division symbol, and you've shown that the quotient of continuous functions is continuous as long as you're not trying to divide by 0. So that works, and all the rest of them work in the same way. Moving on to other kinds of functions and showing that they're continuous, here's a graph of the sine function. And if you were to zoom in at any point on the graph of the sine function, you would find the limit as x goes to any point on the graph is equal to the value at that point. Sine and cosine are definitely continuous functions on all real numbers. Tangent is defined to be the quotient of sine and cosine. Unfortunately, that means that it's not always defined. When cosine is 0, we don't have a value. But on the points where it is defined, it's the quotient of continuous functions, so it must be continuous. Tangent is continuous on its domain, and secant as well is continuous on its domain. That domain is all real numbers minus points which can be written as pi over 2 plus a multiple of pi. So pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2. These are all points at which cosine is 0, so tangent and secant are not defined. But everywhere else, it's defined and continuous. Okay. Complementary to the sine and tangent functions, we have cotangent and cosecant. Cotangent is the reciprocal of sine. Cotangent is the reciprocal of tangent, and cosecant is the reciprocal of sine. So they are continuous as long as sine is not 0. They're continuous on their domain, which excludes all points which are just multiples of pi. So continuous on all real numbers except for pi, 2 pi, 3 pi, etc., negative pi, negative 2 pi, negative 3 pi, etc. Exponentials and logarithmic functions are a pair of families of functions. No matter what base we use for the exponential, the function which takes x to a to the x is going to be a continuous function on all real numbers. You see that it's a nice unbroken curve. At any point, the limit of the function at that point will be equal to the value of the function at that point. Logarithmic functions are inverses of the exponential functions. So the way that that inverse relation is shown in the graph is that the logarithmic function of base a of x is a reflection of the exponential function base a of x within the diagonal line y equals x. So shouldn't be a surprise that if the limit of the function equals the value of the function on this curve and you reflect it through a mirror, that property will still hold true. So exponential functions and logarithmic functions are continuous on their domain. One important thing we have to remember is that logarithmic functions are only defined for positive x's. Our favorite exponential and logarithmic functions are the ones which are taken to the base e. E is an important number, doesn't have a nice decimal representation, but it turns out to be very useful for our purposes. So e to the x and natural log, which is log to the base e, those are continuous functions on their domains. Inverse to the trigonometric functions, we have the inverse trigonometric functions. Their graphs look basically like the graphs of sine and cosine flipped on their end. And as you can see from the graph, we have nice continuous functions. The inverse of sine and the inverse of cosine are continuous inside their domain. Their domain is -1 to 1. And it can't be continuous at 1 because we don't have function values to the left of -1. But we can say that it's right continuous at -1 and that it's left continuous at +1. So here's the graph of cosine inverse. It's basically a reflection of the graph of sine inverse. Therefore, sine inverse and cosine inverse are both continuous. Secant inverse and cosecant inverse are somewhat more complicated as functions, but in terms of their continuity, they're continuous at all of their points in their domain, and they are right continuous at the right endpoints and left continuous at the left endpoints. So those functions are all nice and continuous except at these endpoints where they are as continuous as can be. Tangent inverse and cotangent inverse are defined for all real numbers, and they are also continuous on all real numbers. OK, so there we've run down how we can show that a function is continuous and the kinds of functions which we can assume are already continuous. So all of our favorite polynomial and rational and algebraic functions and trigonometric and exponential and logarithmic functions are continuous inside their domains. If the domain has an endpoint to it, well, then it can't be continuous there, but it will be continuous from the correct definition. So if it's a left endpoint, it'll be continuous as you go to that endpoint, and same thing on the right. Now, how can a function fail, then, to be continuous at a point? It seems like all the examples we've looked at have resulted in continuous functions. How can it not be continuous? Well, we can find out ways that the function cannot be continuous by looking at the equation for continuity and thinking about the ways that that equation could fail to be satisfied. All right, so here's an example. We'll look at a function which is piecewise defined. F of x is x squared if x is in between 0 and 1, and 2x if x is in between 1 and 2. And the question is, at which points is f continuous? Let's think about this for a minute. Let's consider the point a equals 1/2. Is the function continuous at a equals 1/2? Well, at a equals 1/2, we're in this top branch of the domain of the function. F of 1/2 will be 1/2 squared, and all the points which are near 1/2 will also have f of them being their squares. So if you are zooming in on the graph of this function towards a equals 1/2, you will not be able to distinguish it between the graph of the actual x squared function. A bug that's living on the graph right at a equals 1/2 will not know that he's not living on the graph of y equals x squared. X squared is a nice continuous polynomial function, and so this function is going to be continuous at points like 1/2, or points like 1/4, or 3/4, or 9/10, or anything which is in between 0 and 1, not including 0 and 1. Likewise, on the other side of 1, we see that the function takes the definition 2x. So if we try to find out whether this function is continuous at a equals 3/2, we will see that near a equals 3/2, this function is indistinguishable from the plain old y equals 2x function. And that's a continuous function. So this function is continuous at 3/2. And 1 plus 1/4 and 1 plus 3/4, all of those fractions which are greater than 1 are points at which the function is going to be continuous. So the only question really of continuity is whether this function is going to be continuous at 1, at the boundary between the first definition interval and the second one. And for that point, we have to look at the limits from either side. Now from the left, as x is approaching 1 from the left-hand side, the limit is computed by the first rule there, by x squared. The limit as x goes to 1 from the left-hand side will be the limit as x goes to 1 of x squared. X squared is a nice polynomial, so we can use direct substitution, and the limit is going to be 1 squared, which is 1. Now from the right, we have to use the second rule for definition of the function. The limit as x goes to 1 from the right-hand side is the limit as x goes to 1 from the right-hand side of 2x, which again by direct substitution is 2 times 1, or 2. So the limit from the left of the function is 1, and the limit from the right of the function is 2. And since the limits from the left and right disagree, the limit at 1 itself does not exist. Therefore, we can't say the function's continuous at 1. The limit of the function at 1 does not exist. And the graph of the function illustrates this point pretty well. On one side of the point 1, the graph looks like the graph of x squared. On the other side of x equals 1, the graph looks like 2x. So the limit as x goes to 1 from the left is the point 1. The limit from the right as x goes to 1 is the value 2. Since these values disagree, the function fails to have a limit, and so fails to be continuous at that point. Okay, so that's one way that a function cannot be continuous at a point. Let's look at another non-example. This function is f of x is x squared plus 2x plus 1. And the question is, at which points is this function continuous? Well, what kind of function is this? Algebraically, this is what we call a rational function. It's the quotient of two polynomials. And we already know that rational functions are continuous on their domain. They're continuous wherever they're defined. So at which points is this function not continuous? Those would be the points which are not in the domain of the function. And there's only one point not in the domain of the function. It's the point when the denominator goes to 0. That would be at a equals minus 1. So this function is continuous everywhere except for minus 1. We looked at this function before, and we discussed that when x is not equal to negative 1, then the rational function can be simplified. You can divide out a factor of x plus 1 from the numerator, and this just looks like x plus 1. And the way that shows up in the graph is that the graph of this function looks exactly like the graph of y equals x plus 1, except at the point negative 1, where the function is not defined. So we have something that looks like a line with a hole in it. Okay, the question of continuity boils down to whether the limit of the function at a point equals the value of the function at the point. We can see on the graph here that the limit as x goes to negative 1 of f of x is 0. But because negative 1 is not a point at which the function is defined, the function fails to be continuous at negative 1. Okay, one more example. Let's let f of x be defined this way. F of x is 7 if x is not equal to 1, and f of x is pi if x is equal to 1. Question again, at which points is the function continuous? Now, like the first example, the question of continuity is very simple for all points different from 1. If a is not 1, then the function basically looks like the constant function 7. And so the limit of the function at that point will be 7. The value of the function at that point is 7. Function is continuous at that point. The only question of continuity that remains is whether the function is continuous at 1. Now, because this function is constant whenever x is not equal to 1, and that constant is 7, the limit as x goes to 1 of f of x is in fact 7. However, for this function, f of 1 is not 7. We've decided that f of 1 is going to be pi. So since pi, the value, is not equal to 7, the limit, this function is not going to be continuous. Here again we see this on the graph. The function's graph looks like the constant function 7, that is the horizontal line y equals 7, except for the one point that we have changed. We've decided that f of 1 is going to be pi. So the graph looks like horizontal line with a hole in it, and then a point at 1 comma pi. Okay, now if you're paying attention, you'll see that I have not drawn this to scale, because if it were to scale, then 7 would be equal to 2 pi. And we know that's not true. But that's not really relevant. What's important is that we have a limit of the function which is different from the value of the function, and so this function fails to be continuous at the point 1. So what we see is that there are many ways that a function can fail to be continuous at a point, and some of them are important enough to get their own names. We say that a function has a removable discontinuity at a point a if the limit as x goes to a of f of x exists, but it's not equal to f of a. Maybe there isn't an f of a, meaning that a is not in the domain of the function, or there is an f of a, but it's not equal to the limit as x goes to a of f of x. That's a removable discontinuity. Another kind of discontinuity is a jump discontinuity, and that's what the situation where we have a limit from the left as x goes to a and a limit from the right as x goes to a, but these two limits disagree. Okay? There are other ways for a function to fail to be continuous, but these are two important possibilities. And we see on the graph why they get their names. On the left, we have the third example. F of x was 7 when x was not 1, and f of 1 was pi. And we say that's a removable discontinuity because the limit exists, yet it's different from the value. And how is it removable? Well, if I could just pick up that point and put it back in the place where the limit is, then I have created a continuous function. Now, it's true at 1 that the limit of the function at 1 is equal to the value of the function at 1. Okay, we've removed the discontinuity. That's why we call it a removable discontinuity. On the right-hand side, though, we see the graph from the first example, which was a piecewise function with two different expressions on each side of the interval. And we want to know, can we do the same thing? Can we change the value of the function at 1 to create a continuous function? Right now, f of 1 is equal to 1. Is it continuous? No, it's not continuous. Could we change f of 1 to be 2? Is the function continuous now? Well, no, it's not continuous now. We still haven't changed the fact that the limit as x goes to 1 does not exist. What if we split the difference and put f of 1 equal to 1.5? Is it true now that the function is continuous? No, it's still not true because we have not changed the fact that the limit as x goes to 1 does not exist. So on the left-hand side, we were able to remove the discontinuity, but no amount of fiddling with f of 1 is going to create a continuous function on this example on the right-hand side. Okay, so a removable discontinuity can be removed if all you needed to do was change one point. But this is not the case for a jump discontinuity. You can't make it continuous by changing the value at one point. Here's an interesting example. It's a function that we don't see very often but has its uses. This double bracket notation means the greatest integer less than or equal to the input x. So we read this the greatest integer function. I've got some values of the greatest integer function to help you get familiarized with it. If you're plugging in an actual integer, such as x equals 1, the greatest integer less than or equal to 1 is 1. The greatest integer less than or equal to 1.5, well, we round down that 1.5, and we get the greatest integer is 1. 1.9, round that down, and the greatest integer less than or equal to 1.9 is 1. Now, it's not on the table, but think about what the greatest integer less than or equal to 1.99 would be. We would round that down, and we would get 1 again. How about 1.999? That would also round down to 1. And so what you would notice, just by looking at that table, you can also see it on the graph, that as x goes to 2 from the left-hand side, the limit of the greatest integer function will still be 1. Now let's continue to look near 2, but on the right-hand side. What is the greatest integer less than or equal to 2.1? We'll round it down and we get 2. How about 2.01? Round that down and we get 2. So the limit from the right of the greatest integer function as x goes to 2 is 2. All right, so we've shown the function is not continuous at 2 because the limit from the left is 1, the limit from the right is 2. And this is going to be the same situation at all of the whole numbers because that's where you jump from the greatest integer being one number to the greatest integer being the next number. The only thing to be careful about for the greatest integer function is when x is negative, rounding it down makes the number actually larger. So the greatest integer less than or equal to 0.5 is negative 1. The greatest integer less than or equal to negative 1.1 is negative 2. But if you look at the graph, you see we have this nice staircase pattern. And at each integer, we have a jump discontinuity. OK. So we've talked about what it means for a function to be continuous, functions which are necessarily continuous, and ways that a function can fail to be continuous. I want to talk next about an important theorem of continuous functions called the intermediate value theorem. And so here is the intermediate value theorem. I'll read it. It says, suppose that f is continuous on the closed interval a to b, and let n be any number in between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in the open interval a to b, such that f of c equals n. All right. Now there's a lot of math in that pair of sentences there. We have variables. Some of them are true all of the time. Some of them are true for certain values of the variables. And it can be hard to parse a complicated mathematical expression like that. So let me read it again, but at the same time I will draw a picture of what's going on. All right. So suppose that f is continuous on the closed interval a to b. A nice high school colloquial idea about a continuous function is that it doesn't have any breaks or gaps to the graph. And if you want to think about it in very concrete terms, a continuous function on a closed interval is kind of like a piece of string that connects two pegs on the wall. So here we have our continuous function. We label the points x equals a, x equals b, and their values y equals f of a and y equals f of b. The next part of the theorem says let n be any number between f of a and f of b where f of a is not equal to f of b. So we have to assume that these two function values are different. Otherwise, we won't be able to choose something between them. If they're the same, there's nothing between them. But we don't get to choose what n is. N is any possible number between the values f of a and f of b. And if we draw the point with coordinate y equals n, we can make a horizontal line which goes across the plane. And that horizontal line is going to cross the graph of the function over some point with x coordinate c. And that is what the theorem concludes. There is a point c in between a and b where f of c is equal to n. Okay, so f of a is the value at one side of the endpoint. F of b is the value. F of a is the value at one side of the interval. F of b is the value at the other side of the interval. And n is any intermediate value between f of a and f of b. What the theorem says is that that intermediate number n is a value of the function. It is f of something. Okay, it's a very powerful, very deep theorem. We try to prove many theorems in this course, but this is one theorem that we won't be able to prove. If you want to see the proof of that, you have to take a course that we call Analysis 1. Notice that if the function isn't necessarily a nice strictly increasing function, the intermediate value property still holds. This line y equals n still cuts the graph of the function, and we do find a point where f of c equals n. As a matter of fact, in this case, we find 3 of them. This is a c. We could call it c1. Here's c2. Here's c3. And f of all 3 of those points equals n. So what doesn't the intermediate value theorem say? In mathematics, we have a lot of theorems which are called existence theorems, and this is one of those. It says that c exists. It does not say how many c's exist. It doesn't tell you the difference between the case of having 3 c's and the case of having 1 c. And it doesn't give you any idea where that c is, other than it's somewhere between the endpoints. So is it that useful? Well, if you use it in repetition, or if you use it in conjunction with other things, then you can actually strengthen the conclusions of the theorem. For instance, the question about how many such c exist, we'll find out in Chapter 4 that if you combine the intermediate value theorem with something called the mean value theorem, you are able to count the number of times a function takes a certain value. But let's look at using the intermediate value theorem to actually find or estimate the number c where the function takes the value that we want it to take. So let's look at using the intermediate value theorem to find zeros of a function, places where the function must take the value 0. And we'll do it for the example f of x is x cubed minus x minus 1. Now if I had used the function x squared minus x minus 1, it's very easy for us to show that there's a point x where that function takes the value 0, because we can just use the quadratic formula. It turns out that there is a cubic formula, but it's about 10 times as long as the quadratic formula. And you probably don't know that cubic formula, so that's not going to be any use for us. Let's instead use the intermediate value theorem. The function is x cubed minus x minus 1. The interval that we're considering is the closed interval 1 to 2. So let us evaluate or plug in the function at those 2 points. F of 1 is negative 1. 1 cubed minus 1 minus 1. That evaluates to negative 1. And f of 2 is 2 cubed minus 2 minus 1. That turns out to be 5. So f of 1 is negative 1, which is less than 0. F of 2 is 5, which is greater than 0. So 0 is an intermediate number between negative 1 and 5. Now, because this function is continuous, and it is continuous because it's a polynomial, the intermediate value theorem says that there is a number c in between 1 and 2 where f of c is equal to 0. All right, so that's quite satisfying because we've shown just by evaluating the function at 2 points that there must be a third point in between them where the function takes the value 0. Now, that's satisfying, but is it that useful? Is it good to know that the 0 is in between 1 and 2? That's kind of a wide error interval to have. What if we wanted to know the value of c to within, say, a 16th? Can we do that? Well, it turns out that we can use the intermediate value theorem multiple times to get c to that degree of accuracy. We can sort of narrow in on the 0 by something called the method of bisections. So let's take a look at values of the function and the graph of the function. Actually, we don't know too much about this function. We do know already that f of 1 is negative 1, and we know that f of 2 is 5. And barring any other information, we might as well assume that it basically makes a straight line between those 2 points. And we know that in between it's got to cross the x-axis. There's got to be a 0. But beyond that, we don't know so much. Do we know that it's to the left hand? Is it in the left-hand half of the interval or the right-hand half of the interval? We don't know that, but we can test that by taking the midpoint of the interval and plugging that into the function. So if we plug in x equals 1.5, what we get is 0.875. I'll let you check my math on your own. So what we've discovered is that on the interval 1 to 1.5, the function changes from negative to positive. So just like in the original situation, it changed between 1 and 2, now I know that it changes sign in between 1 and 1.5. That's a smaller interval now. I know c to greater accuracy. Okay, but I could do better than that. I don't yet know if it's on the left-hand half of the interval 1 to 1.5 or on the right-hand half of the interval 1 to 1.5. I can find that out by taking the midpoint of that interval, which is at 1.25, and plugging that into the function. This time I'll get negative 0.296875, and I see that the function changes from negative to positive on the interval 1.25 to 1.5. So the 0 has to be inside 1.25 to 1.5. That's an interval of width 1/4. Divided again, 1.375 is the midpoint between those two. Plug that into the function, I get something positive. So now I know that the 0 is in between 1.25 and 1.375. One more time, let's divide. The midpoint between 1.25 and 1.375 is 1.3125. And plugging that into the function, we get something negative again. So now I know that the 0 of the function is in between 1.3125 and 1.375. The width of that interval is 0.0625, which is 1/16. So now I know the 0 with an error of no more than 1/16, which is not too bad for just plugging in 6 points to the function. Now, if you use a calculator or Wolfram Alpha or something else to find the 0 of this function, you'll find out that the first 6 digits of the function are 1.32472. So we only got 1 decimal place of accuracy, but we know we're accurate to within 1/16. So that's one way to use the intermediate value theorem to estimate points at which functions takes a certain value. Let's look at use of the existence argument from the intermediate value theorem to show that the square root of 2 exists. Now, you probably had no doubt that the square root of 2 exists. We have a square root function, but we've actually been taking it for granted that the square root function is in fact a function. That if I plug in any positive number, there is a real number whose square is that number. Right? What is the square root of 2? By definition, the square root of 2 is the real number whose square is 2. And how do we actually know that there is such a real number? Well, here's how we do know. Let's take a look at the function. The function that we're going to consider is the squaring function x squared. Now, we don't know anything, or we're forgetting what we know about the square root function. we do know that x squared is a nice continuous function because it's a polynomial. All right, so in particular, it's continuous on the interval 1 to 2. F of 1 is 1 squared, which is 1. F of 2 is 2 squared, which is 4. And the number 2 is in between those two values, 1 and 4. It's an intermediate value. So by the intermediate value theorem, there is a point C in between the x-coordinates 1 and 2, such that f of c is 2. Now what does it mean for f of c to be equal to 2? Well, this is the squaring function, so f of c is c squared. So we know there's a point C such that c squared is 2, and that number is the square root of 2. Okay, so we can use the method of bisections if we wanted to find estimates of the square root of 2 just by plugging in, say, the midpoint between 1 and 2, squaring it, determining if that's greater or less than 2, then taking the midpoint of the next interval, and so on. But the intermediate value theorem tells us right away that the square root of 2 exists. And in fact, any positive number has a positive square root. Okay, so now that we've seen the kinds of things that the intermediate value theorem can tell us about very specific functions represented by formulas, let's go back to some of the questions that we pondered at the beginning of the class. First question was, true or false, at one point in your life you were exactly 3 feet tall. So by now you've realized that the topic of the day is continuous functions, and an important theorem is the intermediate value theorem. So can this be expressed as a statement of the intermediate value theorem? Well, where is the function in this sentence? The function that we're considering here is your height. Your height is a function of basically your age, or a function of time. So to assert that at one point in your life you were exactly 3 feet tall is the same thing as saying that your height function took the value 3, measured in feet, at some time point t. Okay, and this turns out to be true. So h of t is height, which we have to assume varies continuously over time. Now you could make arguments that the height function is not continuous because the way that we grow is by adding mass, and mass is built up of discrete parts, however small they are. So I guess it would be possible to be 3 feet minus half an angstrom in height, and then immediately after growing by 1 molecule, being 3 feet plus half an angstrom. But that kind of precision doesn't actually get us anything more precise. Doesn't make our lives easier, and we can't measure anything to within half an angstrom anyway, so we will assume that that function is a continuous function. So what are some values of this continuous function, your height over time? Well, if we plug in your height at birth, it is less than 3 feet. If you don't actually know how tall you were at birth or how long you were at birth, that's how they measure it, call your mom. She knows that. And that's definitely less than 3 feet. And for all of us here in the room, our height now is greater than 3 feet. So the height function is continuous, and we have 2 time points, birth and now, and in between those 2 time points, we cross the value 3. So by the intermediate value theorem, there is a point in the interval from birth to now, at some point in time, where the height actually took the value 3. So at some point in your life, you are exactly 3 feet tall. Second question, at one point in your life, your height in inches equaled your weight in pounds. How can we express this in terms of the intermediate value theorem? Well, we need a function, we need a continuous function to be able to talk about the intermediate value theorem. Where is the function in this sentence? There are actually 2 functions in this sentence. One function is your height, which changes over time. The second function is your weight, which also changes over time. To say that your height in inches equaled your weight in pounds is the same thing as saying that there's a point t in time where h of t equals w of t. H for height, w for weight. Now the intermediate value theorem that we have doesn't tell you how to show that one function takes a value which is equal to the value of another function. Intermediate value theorem only applies to a single function. So let's think about how we can express that equation, h of t equals w of t, in terms of a single function. All right, h of t is height, which we're going to measure in inches. W of t is weight, which we're going to measure in pounds. And we'll again assume that these are both continuous functions. To show that these functions have to take the same value at a time, let's take the difference between those two functions. So what we want to show now is that this new function, f of t, takes the value 0. Okay, and 0 is a constant. So we have a single function, f of t. We want to show it takes the value 0. That is something that the intermediate value theorem can do for us. Now, your mom also knows how much you weighed when you were born. And if you take your length in inches, subtract from it your weight in pounds, you will get, I assure you, a positive number. And we all now know how tall we are, and we probably have a good idea of how much we weigh in pounds. And if we subtract those two, I guarantee you we will all get a negative number. So what that means is this function f, the difference between height and weight, is positive at one point in time, our birth, and is negative at another point in time, right now. Therefore, by the intermediate value theorem, there is a point in between those two time points, birth and now, where f takes the value exactly 0. And why is that useful? Because to say that f of c is equal to 0 is the same thing as saying h of c minus w of c equals 0, which is exactly the same thing as h of c is equal to w of c, which is what we wanted to show. There was a point where our height equaled our weight. All right, so how about that third question? Oh, if you hadn't guessed yet, the answer to the second question is true. How about that third question? Right now, there are 2 points on opposite sides of the Earth with exactly the same temperature. Now, this will spark quite a bit of debate, because usually if you look at 2 points on opposite sides of the Earth, it's going to be day on one side, it's going to be night on the other. It might be summer on one side and winter on the other. How is it possible that we have the exact same temperature at 2 opposite points on the globe? Well, I will actually simplify this a little bit and say that there are 2 points on opposite sides of the Earth on the equator with the exact same temperature. So just looking at the equator, which is sort of the belt of the globe, goes around its widest point, we'll find 2 points on the equator on opposite sides of the Earth with exactly the same temperature. So I'm going to measure points on the equator in terms of their longitude. So you know longitude is an angular coordinate. Longitude 0 is at the prime meridian, which is the line of longitude that goes through this observatory in England. All right, so that's been declared to be longitude 0, 360 degrees in a circle. So that would bring you all the way back to England, or to this prime meridian. On the opposite side of the globe from longitude 0 is longitude 180 degrees, and that's the international dateline. So what would it mean? How can we express the statement that the temperature on the 2 points on opposite sides of the Earth at the equator is the same? Well, at one point, we would call the longitudinal coordinate there theta. The coordinate of the point on the opposite side would be theta plus 180. So to say that the temperature at 2 points on opposite sides of the world on the equator is to say that there's a number theta, an angular coordinate theta, such that T of theta, temperature at theta, is temperature at theta plus 180. All right. Now, again, like with all the other functions we've considered, we have to assume that temperature along the equator is a continuous function. And I think that's a reasonable assumption, because if we think about temperature, we don't have big jumps in temperature at any point. The temperature is nice and smooth. It doesn't make large gaps as you move around. Kind of how heat flows around, it averages itself out, and it's nice and continuous. So how could we assure that there's a number theta such that T of theta equals T of theta plus 180? That's, well, like before, let's take the difference between T of theta and T of theta plus 180. And we'll call that difference function f of theta. Now we know very little about the temperature as we circle the globe. But we do know that at longitude 0, the prime meridian, f of 0 will be T of 0, temperature at the prime meridian, minus the temperature at the international dateline. Likewise, the temperature at the difference function f at the international dateline will be equal to the temperature at the international dateline minus the temperature at coordinate 360. Now, because we're going all the way around the world, the temperature at 360 is the same as the temperature at 0. These are the exact same point. So f of 180 is T of 180 minus T of 0, whereas f of 0 was T of 0 minus T of 180. So f of 0 and f of 180 are opposites to each other. We don't know that f of 0 is positive, but if it were, f of 180 would be negative, the exact opposite. If f of 0 were negative, then f of 180 would be the opposite. It would be positive. So whether f of 0 is positive or negative, the point on the other side is going to be the exact opposite. That means that 0 is in between f of 0 and f of 180. And by the intermediate value theorem, there has to be a point theta in between 0 and 180 where f of that point theta is equal to 0. And there you have it. We do now know that there are points on opposite sides of the world which have the exact same temperature at the same time. So those are all things that we can use the intermediate value theorem to demonstrate. So let's summarize what we've talked about. We brought out this notion of continuity of functions continuous at a point if the limit of the function at that point agrees with the value of the function at that point. And in terms of the graph of the function, we say that it's continuous if we don't see any breaks in the function. And we can also say that the function is continuous at a point if small changes to the input of the function near that point result in not large changes in the output of the function at that point. And most of the functions that we're going to deal with modeling things in nature, like height, like weight, like temperature, those are going to be continuous functions. And we can use this property that the limit of the function at any point equals the value of the function at that point. Because of that, we can use the intermediate value theorem, which is a basic property of how real numbers and functions of real numbers actually work. We need this theorem, and we will use it a lot. So the last of these the things that we need to consider is the intermediate value theorem. Intermediate value theorem is a very basic, fundamental fact about continuous functions, and it's something that we will need and use a lot.